Hey there, it's Shannon MATHCHICK Myers, and today we'll be taking a look at numerical integration. Some elementary functions do not have antiderivatives that are elementary functions. A few examples are e to the x squared, cosine at x over x, and the square root of 1 minus x cubed. That's not all of them, obviously, but e to the x squared is a pretty famous one. And for integrands which contain expressions like these, we can use numerical integration. Aren't you excited? Instead of the fundamental theorem of calculus, which is your regular definite integral that you're typically doing. Let's assume that f is continuous and positive on, sorry about the typo, the interval, closed interval from a to b. The definite integral from a to b of f at x dx represents the area of the region bounded by the graph of f and the x-axis from x equals a to x equals b. So we can partition the interval closed from a to b into n subintervals, each of width delta x equal to b minus a over n, which is a regular subinterval, such that a is equal to x0, which is less than x1, less than x2, less than all the way until we get to less than xn, which is the right endpoint, b. So if you think about this, you can just kind of make sort of a, just a random graph. Let's just say a is here, so remember a is x0, and then we have subintervals of equal width, trying to make them equidistant, and then this next one would be x1, x2, x3, and then the last one would be xn, which was equal to b. Cool so far? Now, we'll just make a random shape. Doesn't need to be anything in particular. So let's just say we've got a shape that goes something like this. Cool so far? And then what will happen is that we will have these, instead of making the rectangles like we did before, what we would do is we would start with this left endpoint and make trapezoids. Pretty cool, huh? And so, continuing, it would look something like this. And just like with the fundamental theorem of calculus, the more trapezoids that you have, the narrower the widest subinterval gets, which is the norm of your delta, and you will end up with n going to infinity. Cool, cool? So the number of rectangles going to infinity causes the width of the widest subinterval to go towards 0, and vice versa. Groovy? All right, so now let's just take a look at these measurements, okay? And so if we look at these heights, right, they're going to be your function value. And so if I do this one in pink, the pink would be f at x0. And then I can do this other one in brown. That one would be f at x1. Cool so far? And so on and so forth until you got to the end. And the cool thing is by having a regular subinterval, right? This here, the red, is going to be your delta x. And remember that we're going to have delta x equal to b minus a over n. Good so far? Now, the only other thing to put together is the area of a trapezoid. I like to think about the area of a trapezoid as the average of the bases times the height. The height is what makes a right angle, right, with the bases. So here it's a little different because it's like a trapezoid on its side. So the bases are actually these f of x0, f of x1, etc. And so if I do the average of these bases, this is for area of our trapezoids, f at x0 plus f at x1, this would be for I equal to 1 over 2, right? But what's the height going to be? It's going to be times delta x, right? Times delta x. Cool so far, which we know is b minus a over n. So this is the area of the first trapezoid. So our I would equal to 1. The area of the ith trapezoid will be, I'm going to take the 1/2 out in front, and then we'll have f at x sub I minus 1 plus f at x sub I, and then times our delta x. Good so far? I'm going to keep it as delta x for a little while, and then we will plug in our b minus a over n. Groovy? So what we have is our area equal to delta x over 2, combining the delta x multiplier and the 1/2, neither of which have an I, times f at x0 plus f at x1. That's the area of the first trapezoid. Good so far? And then the next trapezoid height or bases would be f of x1 plus f at x2. Good so far? And then it's going to keep repeating, right? So you keep going until you would get to the last trapezoid, which would be f at x n minus 1 plus f at x n. Good so far? So remember, this here was the height measures, which are really the bases of the first trapezoid, and then bases of the second trapezoid. So do you see what's going to happen? You're going to end up doubling all of the function values except for the very first one and the very last one. Isn't that kind of cool? All right, so here's what'll shake out. We'll end up getting our delta x over 2 times. We'll have f at x0 plus 2 f at x1s plus 2 f at x2s plus dot 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 2 f at x sub n minus 1s plus f at xn. Cool, cool? All right, so here's the evil plan. Do you see how all of these in the middle are multiplied by 2? We want to make a summation so we can make a nice cool formula for this. So if we take our delta x over 2 and we multiply it by f at x0, we're good on the x0 because we can make that summation start at x equal 1. Now, we also need to add that f at xn. Cool? So we basically are looking at our f at x0 and f at xn. They're taken care of. But here's the deal. We don't want to bring the summation to n minus 1. We want to bring it to n so we can send n to infinity and it'll all look pretty. So here's the deal. I am going to subtract 2f at xn's here. Okay, so far? Now, what I'll have left is this. I'll have 1/2 times 2 at fx1 plus 2 at fx2 plus dot 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 plus 2 at fxn. So here's those 2 f at xn's that I added in here. Notice that 1/2 is multiplied to both. All right, so we've balanced everything out. Good so far? And then that'll be times delta x. I'm bringing the delta x to the end of it. So now we will have 1/2 times f at x0 minus f at xn when we simplify times delta x. Do you see that 1/2 will divide out all of those 2 coefficients in the second part of it? So that 1/2 simplifies all those expressions and gives them a coefficient of 1. So we can then write it as the summation from I equals 1 to n of f at xi times delta x. Cool so far? And then we're going to leave that other one alone. We're going to rewrite this one as 1/2. We know f of x0 is the same as f at a minus f at xn is f at b. And then we're going to multiply it by b minus a over n. That's our delta x. So that's our delta x. And then we will have plus the summation as I goes from 1 to n of f at xi times delta x. Groovy? Now the last thing we need to show is that the limit as n approaches infinity of this whole thing we have to show that this limit approaches the definite integral. All right? And so here, this first limit, do you see, because of this n denominator, will end up being 0, right, when we apply the limit. And then the second limit will be which will be the integral from a to b of f of x dx. Cool, cool? So that's the proof for it. What we want to remember here is that if f is continuous on the closed interval from a to b, the trapezoidal rule for approximating the integral from a to b of f of x dx is equal to, so the integral from a to b at f of x dx is approximately equal to b minus a over 2n, combining that delta x times the 1/2. And then that will be times f at x0 plus 2 f at x1 plus 2 f at x2, and then all the way down to 2f at x n minus 1 plus f at xn. Groovy? Note the coefficients, as you may have noticed, in the trapezoidal rule have the following pattern: 1, 2, 2, 2, dot, 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 all the way down to 2, 1. Cool, cool. And then as n approaches infinity, the right-hand side approaches the definite integral from a to b of f at x dx. Groovy? So let's do a problem. All right, so I wrote the formula again for you. Use the trapezoidal rule to approximate the definite integral. So here we go. For the first one, we want to use the trapezoidal rule to approximate the definite integral. So let's pull out our technology to make it easier to do this. I'm going to go to y equals, and then we will graph x squared over 4 plus 1 and then we are interested in the x values between 1 and 2. So we'll keep our graph about here. Good so far? Now, we are being asked to use 4 rectangles to do this. And so, if we take, kind of a picture of this graph, okay, so we are being asked to use 4 trapezoids to approximate this area. And so, how do I figure out how many we need? Well, we're going to use delta x is b minus a over n. Well, n is 4, right? B is 2, a is 1. So we'll have 2 minus 1 over 4, which is 1/4. Cool so far? And so what this will look like visually would be, you would start at that x0, which is 1, and then you'd be about here, halfway in between, and you'd have 1 of your trapezoids, right? Something like this. And then the next trapezoid. We good? Cool, cool. And so we're approximating our region by using these trapezoids here. Cool so far? All right, excellent. It's always nice to have a visual. It's easier to visualize with the trapezoidal rule than Simpson's rule, so we're not going to go as much into depth with Simpson's rule. Okay, so now, here we go. Now, if we use our formula, right, we are going to, I'm going to click on this graph. By the way, this is a cool little app called Graph and Calc, 83, I believe. And then we just want to calculate some values. So we want to know what the output when x is 1 is, all right? And so here we go. So for our formula, which we have here, right, we're going to get the integral from 1 to 2 of x squared over 4 plus 1 with respect to x is approximately, so using our b minus a over 2n, we'll have 2 minus 1 over 2 times 4 times, we're going to have f at 1 plus 2 times f at 1 1/4, right? Which is, I'll just write it as 1.25, or approximating anyway, plus 2 times f at 1.5 plus 2 times f at 1.75, that's adding an additional quarter each time, and then plus f at 2. Cool so far? Awesome. This will equal to 1/8 times. Now I'm going to use the calculator to get these function values. F at 1 is 1.25, all right? And then f at 1.25, whoops, sorry, oh, we can delete. Oh, we have arrows. Perfect. 1.25, enter, is going to be 1.3906 plus 2 times, when I enter in 1.5, I get 1.5625 plus 2 times, entering in 1.75, we get 1.7656, and then entering in f at 2, we'll just get 2. So we'll take that one away for a moment and just kind of check out what we have, right? Okay, so now, here we go. Let's add them all up. I guess we needed this, huh? So what we'll have is, we'll have 1/8 times 1.25 plus 2 times And this will give us approximately 1.5859. And we don't need to put square units because we're approximating the definite integral. So now if you went, let's see how close we are, if you went into math and then f function integrate, and we went from 1 to 2, I mean this is one that we can do on our own, right? As well, using the fundamental theorem of calculus. Look at that, we get 1.583333. So when we check it, it's a little bit different, but that is okay because it's an approximation and we only used 4 rectangles, right? So had we used some more rectangles, we probably would have gotten a better approximation. I'll just copy this one here. Check. Groovy? All right, so we are good to go. That again was the trapezoidal rule. All right, so for Simpson's rule, Simpson was all about using quadratics, all right, parabolas to approximate. So I'm just going to give you the theorem, all right? Start it up here. Sorry, I forgot to write it in. All right, so here we go. Same premise. Let f be continuous on the closed interval from a to b. And let n be an even integer. So this one, n has to be an even integer because of the way the pattern is. So Simpson's rule for approximating the integral from a to b f at x dx is the integral from a to b of f at x dx is approximately equal to b minus a over 3n times f at x0 plus 4 times f at x1 plus 2 times f at x2, 4f at x3, and you keep going. The 2, 4, 2, 4 keeps going until you get to 2 times f at x sub n minus 2 plus 4 times f at x of n minus 1, and then plus f at x sub n. Cool, cool? All right, so let's see how it works. We're not going to prove this one. The proof is in your book if you're interested. All right, and so here, again, we'll go ahead and we'll make a picture of the graph And we're interested between x is 1 and x is 4. So we'll move this in a bit. Okay, so we have a good zoom from our interested zones around x, okay? So here we go. We'll go into calculate, and then first let's set it up. So the integral from 1 to 4 of 4 minus x squared with respect to x is approximately. So applying our rule, n is 6. This is going to be b minus a over 3n. And so, just really quick, delta x, right, is still b minus a over n, which in our case will be 4 minus 1 over 6, which will be 1/2. So each successive x value would be adding 1/2 to the previous. And so over here, we'll have b minus a over 3n for the formula, so 3 times 6. And then times f at 1, right, plus the second one will be a 4 times, so 4 times f at 1 plus 1/2, which is 1.5, plus 2 times f at another half, which would be f at 2, plus 4 times f at 2.5, plus 2 times f at 3, plus 4 f at 3.5. This is why you need an even number. And then plus f at 4. Cool so far? All right, so now let's go into get our y values here. All right, so we want to find f at 1, which is just 3. So we'll have 4 minus 1, which is 3 over 18. I'll just write it like that for the moment, simplifying the multiplier. And then f of 1 was 3. Then we have 4 times f of 1.5. That's 1.75. Plus 2 times f at 2. So f at 2 is 0. Plus 4 times f at, what are we at? 2.5. 2.5. And we'll get negative 2.25. That's okay because we're not finding the area. If we were finding the area, we would have to, use the absolute value of those negatives, right? It would be completely unbound at this point because we haven't been given another horizontal line to bound it. But anyway, we're good. Plus 2. F at 3 is negative 5. And then plus 4 times f at 3.5, which will be negative 8.25. And then we're finally at f at 4, which is negative 12. Excellent. All right, so now this will be the 3/18 is 1/6. Okay, so we'll quit out of here and then we'll go into adding this up. So we will have 1 divided by 6 times. And this gives us -9. Cool, cool? All right. Well, I hope you had a wonderful morning, afternoon, or evening whenever you're watching this show. And hey, if you like what I'm doing, go ahead and click on that subscribe button, the like button, maybe share the video, and I'll see you next time. Bye.